In section 4.4, we're going to take a look at a concept called concavity, and then we'll also take a look at something called the second derivative test, which, if you remember from section 4.3, we had a first derivative test. Now we have a second derivative test. We have a couple of objectives here. One of them is to determine intervals in which a function is concave up and down, find points of inflection, and then apply the second derivative test. So just 3 short things in this section. It's actually a fairly quick section. All right, so first off, terminology, definitions to be specific. Concavity. Basically, what we have here is concavity is a way to measure the rate of change of the increase or the decrease of a function. Right? Geometrically, what it does is it addresses the shape of a graph and how that shape is changing. Right? All right, so more specifically, in section 4.3, we took a look at the idea of increasing and or decreasing functions. But what we didn't address is that there are a couple different ways that increasing can occur. You could have a function that increases in this manner, or you could have a function that increases in this manner. Right? Now, both of these functions are increasing functions, so both of these functions would have a positive first derivative. But the way that they're increasing is different. This graph on the left, as we move further in the positive x direction, the graph gets steeper and steeper and steeper. And so as the x values increase, the increase of the graph is increasing. Right? Whereas, or by contrast, on the graph on the right, as we move further on the positive x direction, the increase is actually decreasing. The graph is getting flatter, if you will, whereas the one on the left was getting steeper, the one on the right is getting flatter. And because these two behaviors are different, mathematicians wanted to find a way to quantify them. Okay? Now, remember, when we're looking at this, what we're looking at is a picture. And if you have the picture, it's easy to see that these two things are different. Right? But think back to when a lot of this mathematics was developed. Right? When it was originally developed, we didn't have any sort of a graphing tool, so all graphs were hand-drawn. So simply knowing that a function was increasing was insufficient to really draw the shape of the graph accurately. We didn't know how it was increasing. Right? So what came out of that is the idea of the study of concavity. Now, when a graph is said to be concave upward or concave up, right, the shape of the graph is such that all of the tangent lines to the curve lie below. So see how these tangent lines are underneath the graph as we draw them? Whereas with a function that is concave downward or concave down, all those tangent lines are going to lie above the curve. Now, I know what you're thinking. Well, what if you had a graph that did both? So yes, you could have a graph that changes concavity, where you could have sections of the graph where the tangent lines would be above, and then you could have sections of the graph where the tangent lines would be below, and so you'd have intervals of concavity. Intervals where it is concave upward, concave up, shaped like a cup, okay? Or intervals of concave downward, concave down, shaped like a frown. Okay? So, I have concavity. Concavity is a way to describe the behavior of a function. Right? Remember, graphs are hand-drawn. I need to be able to describe it. Concavity is a way to describe how the change is occurring. Is the first derivative increasing? Because if the first derivative is increasing, tangent lines lie below the curve, where we say that the curve is concave upward. Is the first derivative decreasing? If so, then tangent lines lie above the graph, and the graph is said to be concave downward. Right? So then how do I know whether the first derivative is increasing or the first derivative is decreasing? Right? I'm going to use the second derivative as a measurement of the change, the rate of change of the first derivative. Right? So let f be some function whose second derivative exists on some open interval I. So we're going to have some interval a to b, that's our open interval I, and the second derivative exists for all values in that interval. Now, if the second derivative exists for all values in that interval, then I can use this test for concavity. And the test for concavity simply says that if the second derivative is positive, then the graph is concave upward. And if the second derivative is negative, then the graph is concave downward. Now, I know what you should be thinking right now is, hey, this looks like the test for increasing and decreasing. And essentially it is. The test for concavity is the same process as the test for increasing and decreasing. It's just the test for increasing and decreasing uses the first derivative, whereas the test for concavity uses the second derivative. But we essentially do the same thing. Okay. All right, so before we can actually start working with finding these intervals where it's concave upward or where it's concave downward, we need to discuss one more term, and that is a point of inflection. If you have a graph like the one we talked about, where the concavity isn't consistent, where the concavity changes, then a point on a graph where the concavity changes, either from upwards to downwards or downwards to upwards, doesn't matter which change, is called a point of inflection. Okay? Now I want to highlight something. It is a point on a graph. Simply because concavity changes does not mean that you have a point of inflection. Right? You could have a graph that looked like this. So you have some function that looks like this. On this piece over here on the left, the tangent lines are below, or we would say that this is concave upwards, or concave up. The piece over here on the right, the tangent lines are above. So we would say that this is concave down, or concave downwards. Okay? The concavity changes when x equals 0, but this graph has no point of inflection because there is not a point on the curve, because there's a vertical asymptote. Oh, I want this one. There's a vertical asymptote there. There is no point on the curve where the concavity changes. Okay? So sometimes we have points of inflection, sometimes we don't. Right? In this first graph over here on the left, we have a lovely point of inflection right there, a POI, a point of inflection, because the graph changes from concave upward to concave downward at that point. Right? Another point of inflection where the graph goes from concave downward to concave upward. And then another point of inflection where it goes from concave upward to concave downward. Okay, so if the graph has a point where the concavity changes, up to down, down to up, doesn't matter, it just has to change there, then we say that we have a point of inflection. So now that we know what a point of inflection is, what concavity is, how do I find it? All right, so a point of inflection is a point C comma f of C on a graph of f. And if that is a point of inflection, then either the second derivative is equal to 0 or the second derivative does not exist at that value C. So wait a second. This is an if-then. So what we're going to do to find these points of inflection is so to find these points of inflection and to find these intervals of concavity, one, we are going to find all values where f double prime of x does not exist, or where f double prime of x is equal to 0. 2, we are going to test the intervals formed by these values. And then 3, we're going to divide it up. Okay? So it's concave upwards from here to here, concave downwards from here to here, and these are my points of inflection. Okay? All right, so let's take a look at an example. Maybe this will kind of solidify if we do an example. Okay? All right, so let's take a look first off the language. Determine the points of inflection and discuss the concavity of a function. Now this phrase right here, discuss the concavity of, simply means describe the intervals where it is concave upwards and the intervals where it is concave downwards. Okay? Determine the points of inflection means to find all those points on the curve where the inflection, where the concavity changes. A point of inflection. Remember, a point contains both an x and a y. So a point of inflection isn't when x equals 3. A point of inflection is the point 3 comma when whatever the functional value is there. Okay. All right, so the process is first to figure out our test points or our candidates for points of inflection. Our candidates or our test points for points of inflection are anywhere where that second derivative does not exist or where that second derivative is equal to 0. So before I can do anything, I need my second derivative. In order to get the second derivative, I have to find the first derivative. So the first derivative of x to the fourth minus 4x cubed is going to be 4x cubed minus 12x squared. And then we'll take our second derivative. Our second derivative is going to be 12x squared minus 24x. So this will be the function that I'm working with, the second derivative of f, okay, to define these points of inflection and define these intervals of concavity. Okay? So step 1, our candidates. Okay? Now it's very tempting to call these things critical values because we're finding where it doesn't exist and where it's equal to 0. The second derivative doesn't exist and the second derivative is equal to 0, but these are not critical values. Critical values specifically means, the definition of a critical value means the first derivative is equal to 0 or the first derivative does not exist. Here we're working with the second derivatives. So if you say critical values are critical numbers, you're talking about first derivative stuff, and this is second derivative stuff. Technically, I've never seen a name for these points. I call them candidates. They're candidates for our points of inflection. I've never seen a name for them, though, that is consistent across all calculus textbooks. So it's where the second derivative is equal to 0 or where the second derivative does not exist. Now, I'm going to treat this the same way I do my first derivative stuff, though. I'm going to find the does not exist ones first. Are there any values of x for which this second derivative would not exist? Okay? So when I'm looking at the second derivative, I'm seeing a polynomial. I see no division by 0 errors. I see no roots of even roots of negative number errors. I see no weird trig stuff, no weird logarithm, no weird exponential, anything going on. So I'm going to say that there are none of these. There are none of the does not exist because I can't think of a single x value that would make that second derivative not exist. Now I'll look for when is the second derivative equal to 0. So I will set the second derivative equal to 0. I'll solve. This one looks factorable. That's going to give me 12x times x minus 2 is equal to 0. This gives me x equals 0. This gives me x equals 2. So I have two candidates that I'm going to test for being points of inflection. So I'll draw out my number line just like we did for the first derivative stuff. I'm going to put on there my two candidates. That's going to give me 3 intervals. Okay? And now I'm going to test each of these 3 intervals, but I'm going to test each of these 3 intervals not for increasing and decreasing. I'm testing for concavity. So interval number 1. Okay? A point on interval number 1, I'm going to use -1. I'm going to find out what is the value of the second derivative at -1. So that is going to be 12 times -1 squared minus 24 times -1. Let's see, that's going to give me -12. So the first interval is going to have a negative value. That means that f double prime is less than 0. Now, according to the definition way back up here, second derivative negative means it is concave downward on that interval. So what we just showed is that the first interval there, left of 0, is the graph being concave downward. Now we'll test the second interval. The second interval, I'm going to use the value 1. So interval number 2, I'm going to find the second derivative at 1, which is going to give me 12 times 1 squared minus 24 times... You know what? I just realized I made a mistake. That's positive. That's positive. This is actually positive 36. So let me go back and fix that real quick. I lost a negative there. Since the second term is positive and the first term is positive, this is 36, which means this is greater than 0. And greater than 0 means concave upward. So we're concave upward on that first interval. Sorry about that. Okay. Second interval I'm working on here, f of 1, so that's 24 times 1, so that's going to give me 12 minus 24. This is the negative 1, negative 12. So our second interval, f double prime, our second derivative is less than 0. It's negative. The second derivative is negative, which means we're concave downward. Right? Now I'll test the third interval, interval number 3 over there. I'm going to use the value 3. So third interval, I'm going to find f double prime of 3, which is going to give me 12 times 3 squared minus 24 times 3. Okay. 12 times 3 squared is 9 times 12. 9 times 12 is 9108. Minus 24 times 3, 2040, 60, 72. So positive. So our second derivative is positive on that interval. And because the second derivative is positive, that means on that interval concave upward. Right? Now the last thing I have to do is I have to figure out what's happening here and here. Does concavity change at 0? And if concavity changes at 0, then we have an inflection point, or we have a candidate for an inflection point. Well, to the left we're concave up, to the right we're concave down, so concavity does change. Okay? Concavity does change at 0. Okay? So we're concave up from negative infinity to 0. We're concave down from 0 to 2. And then we're concave up again from 2 to infinity. And it looks like we're going to have points of inflection at x equals 0. And then f of 0 would be also 0. And where did I get that from? Plugged in 0 to that bad boy. Okay. And we have another point of inflection when x is 2. And f of 2 is going to be plugging 2 back into here. 2 to the 4th is what, 16? And 2 cubed is 8. 4 times 8 is negative 32. 16 less 32 is negative 16. Okay. Now, if you wanted to, you could also represent these as more of a traditional point and say 0, 0, and 2, negative 16. Okay? Now, I feel very uncomfortable with this because it's my first one, so what I'm going to do is I'm going to go take a look at the picture and see if the picture matches what we're saying here. All right, so get rid of that graph. We need the graph of f of x equals x raised to the 4th minus, was it 4x raised to the 3rd, I think? Yes. And so supposedly, I should end up with a graph that is concave up left of 0, concave down from 0 to 2, and then concave up from 2 to infinity. Okay. So let's see if I can see what I'm seeing here. Whoa. So left of 0, concave up, tangent lines would lie below that graph, so I feel good about that. 0 to 2, tangent lines are above. 2 to infinity, tangent lines are below, so I feel pretty good about this picture. Now, one thing you might remember about Desmos is it can find intercepts and it can find maxes and mins, things we did last section. What it can't find, what it doesn't have the ability to find, is points of inflection. So there is a point of inflection there at 2, comma f of 2. But it's something that the graph can't, or that the tool can't find for us yet. I'm sure they're working on it. All right, that brings us to the end of the first video for section 4.4. I'll make another one. We'll do some more problems. I'll see you back here for part 2.